bottom, you will drop this much in height, and that means that this much energy is going to come out of potential, and this much is going to then go into kinetic. Okay? They will all eventually reach the same speed. This is assuming, of course, this is a frictionless incline, right? So they will all have the same final speed. This one, and this one, and this one. All the same speed. Different accelerations, different times. That's what kinematics helps us to figure out. But if we're talking just energy, energy doesn't deal in any of that. Energy just says you drop down through the same height, you get the same amount of energy from potential energy, it's going into kinetic energy. Are there any questions on that? Okay, so there's an example. There's a guiding force in there, and gravity is, of course, doing its thing. Gravity only cares about your height above the ground. It doesn't care about anything else. Let's now do a problem that is so complicated we never could have attacked it before. Roller coaster loop-de-loop. We're going to start a roller coaster car up here at rest. The height of the hill here is 30 meters. We'll say it's frictionless once again. That's important because friction is not a guiding force. Friction is not going to act 90 degrees to your motion. Okay? Friction's going to do work, and we have yet to figure out how to get that in there. This thing is going to slide down a loop-de-loop, and the radius of this loop-de-loop is 10 meters. So the object is going to go here. I'll call that point A. That'll be the top of the loop. Let's look at it going down the side of the loop. That's point B, I'll call that. And then let's look at the exit point, which I'll call point C. And my question is simply going to be, find the speed of the roller coaster car at each of those points. Now, before I do it with energy, let me talk about why it would be very hard to do this with forces. Okay? So, even without friction, there are still two forces that will always act on this mass, on this roller coaster car. Gravity is always downward. So, if this is the force of gravity, as this thing goes down, it'll always be downward like this. But the normal force is perpendicularly away from the motion, so that's going to look like this. It's always pushing away on the track. So if I wanted to find the net force at any given moment, I need to do the vector addition of the two. It would look like this. I need to find the vector addition of these two. Which is, of course, constantly evolving in time. So the size and direction of the net force would be all over the place. And that's even if I knew the exact shape of the track, which I don't. So this is pretty much, with the forces method, forget it. You have a net force and acceleration that are changing constantly with time. Those are the kind of things we don't do. We have the constant acceleration equations for when the acceleration is constant, and you can't use it otherwise. But energy is going to be very, very easy to use here, because we know that gravity, the only thing we have to do is track height above the ground. That's easy enough. The normal force is a guiding force that's never going to make it go faster or slower, and that's all we have. So we know that no matter what happens, no matter how many times you have to trade energy between the two forms, that the total should always be the same. So no matter which point we look at, the energy should all be there. The initial point and points A, B, and C, we should have the energy all there. So let's go ahead and make a little chart here. We'll fill in what's H and what's V at the initial point and points A, B, and C. Those, after all, are the two active ingredients in the energy, right? How fast is it going and how high it is. The active ingredients, by which I mean, of course, that they might change during the problem. I should, of course, mention that in its current form, everything has an M, so M is going to cancel. We don't even need the mass. There'll be one in every term, so it just goes away. So I don't actually need to give you that. That's common in these problems, by the way. So if you don't get given the mass, just trust it'll cancel. All right, so let's set a 0 height here. Lowest height of interest is point C, so let's set H equals 0 down here. What's our initial height? 30. Put the units in the header here, so I don't have to put them everywhere. 30 meters. What's the speed there? 0. So that right there establishes how much energy is in the system. It's non-kinetic energy to start with because the object's at rest, but you have some potential energy because you're 30 meters above the ground. That's where you get the energy that will then have to be conserved from there. So let's go to point A. How high are we above the ground at point A? 20. We're one diameter of the loop-de-loop, right? Radius is 10, diameter is 20. That's all we need to know. We don't need to know that you went down first and came back up. Who cares? Okay, we're just tracking height above the ground. So we can solve for what's the speed. How do we do that? We just make sure that the initial energy is all present at point A. So try it at home. Just a little bit of algebra. But you can probably tell me if that you're lower, right? If you went from 30 meters to 20 meters, you don't have as much energy and potential. Where did it go? It went into kinetic energy. So now you're not at rest anymore. If you solve for this, you will get 14 meters per second, roughly. Let's round it off. And here, let me put the units in the header again so I don't have to put them on everything. Just like that. Okay, how about point B? How high am I? 10 meters. Okay, so even less is going to be in potential energy. So where is it? It's in kinetic, right? Should I be going faster or slower than 14 here? Faster. Solve for, you get about 20. It's rounded off, it's not exactly 20. Okay. And finally, what's my height at point C? 0. So now I don't have any energy left in potential. It's all in kinetic. I'm going to be going the fastest of all of these points, 24. Okay. Now how do I do this? Again, you can certainly work your way down, or you can just always compare back to the initial. Because the initial is going to be equal to A, B, and C. The only reason I might refer back to the initial for each one of those calculations is simply because I don't want progressive round-off error to trip me up, right? So there it is. It's that simple. All right, let me label these guys. I found here you are going 14 meters per second. Here you're going 20, and here you're going 24. How fast am I going right about here? 14. 14. Same height, same speed, right? Same proportion of potential energy and kinetic energy. Same height, same speed. That's really all these come down to. You're trading height for speed. Height is the active ingredient in potential energy, and speed is the active ingredient in kinetic energy. So when you're trading kinetic energy, potential energy, it's a way of tracking the fact that if when you go lower, you go faster. When you go higher, you go slower. That's it. Okay? And this is our way of treating that. When you get right down to about here, how fast are you going? 20. How fast are you going right before you go up the loop-de-loop? 24s. At that point, once again, you have no energy in storage. It's all kinetic. But then you start to go higher again. And by the time you reach the loop going the other side, you're going 20 again. You get to the top, you're back to 14 of the loop-de-loop. You come back down to the other side, going 20 again, come back down, going 24. Right? That's it. You're trading height for speed. So it's very easy and very powerful to use this. Are there any questions on that? Yeah.
When we're doing the interaction gravity, it was MGH. H is how far we travel, or how far we come
It's your height above the ground at that moment. Okay, it's not a displacement; it is a index of location. So our height goes from 30 to 20 to 10 to 0, back to 10, back to 20, etc. If you look at where the H came from, it originally came from a delta H, right? But we split apart that thing into initial and final potential energy, and they're both H there. Are there any other questions?
I kind of got lost how you calculated the V, the velocity.
How did I get this?
Yes.
So all I did was I set that the initial energies equals the final energy. So if you want to see an example, mgh initial plus 1/2 mv initial squared equals mgh at point A plus 1/2 mv at point A squared. So this is 30 meters. This is 0 meters per second. This is 20 meters, and I'm solving for this. And the answer is 14. Yeah?
Why not just use the K equals KG?
That's what that is.
Yeah, I know. I'm just saying as a shortcut. So you were saying that you're not taking the displacement of the height?
That's right.
You're taking the actual height? So I plugged
Yeah.
in 10.
So you want to use this thing here? Is that what you're saying?
No, I'm asking clarification of what Scott asked that question.
Well, see the
Because
problem.
I used 10 to get 14 on point A, and I'm now confused.
Sorry, the machine's a little bit loud.
Oh, I used 10. I used the difference, I guess.
Well, I mean, that I think is a lot harder, right? Because if you're going from here to here, delta H is minus 30, and then when you're going from here to here, it's plus plus 20 on top of that,
Oh, I see.
and then it'd be like from here to here. So you have to like constantly like track of the motion. What I'm saying is just let's look at measure its height above the ground and just index it from some common zero value, right? And so that's the whole point of moving from the work method to the energy method. Is then work, you're worried about displacement, and we're trying to find is this new quantity where we just have to index the location of the object from some reference point.
But so plugging, if you use K equals BG, then I plugged in 10 for the height to get 14.
So in this calculation here,
Yeah.
okay. So we're comparing this point here and this point here. So where you got a 10?
I basically moved, it's like V squared equals the square root of 2 times 9.8 times 10 is 14.
Sorry, I'm not following. So you calculated the change in kinetic energy?
I mean, I don't know. I'm just trying to figure this out. So
I just having a hard
I
time
know,
hearing you.
yeah,
when
so
you're reading a bunch of
KE
numbers.
is 1/2 mv squared, right? Equals mgh.
KE, sorry, go a little slower. KE.
Equals 1/2 mv squared.
Uh-huh. And you use what in there?
Equals PE, which is mgh, right? So.
Well, here's your problem. Is this the initial or the final?
This
Final at point A? Okay, this is point A.
Yeah.
And then, oh, I see. And then you basically set what you basically did was you set the 0 here, right? So you said that this was 0, therefore you don't have any potential energy at the end. And then above that, you'll have a height of 10, right? So mgh initial, and you said this was 10, you're basically assuming that h final is 0. So that's fine, except for you haven't set h equals 0 at your lowest height of interest, so you're going to have to continually move it when you go on to the next parts. So my whole point was that you pick h equals 0 down here so you don't have to move it, right?
Yeah.
So I'm perfectly okay with the fact that the initial height is 30 and the final height is 20, right? So that neither of them are 0 because I want to set that the 0 height is here, right, at the bottom. What you've essentially done here is you said that the initial energy is all potential energy. At the end, it's all kinetic. You don't have any potential energy left, but that is basically setting your 0 up here, right?
I mean, I guess what I really did is if you take the top, what you wrote at the top, MGHI, right, that whole. If you subtract MGHA, you're getting 10 as the total height.
Yes, you are.
And that's what I use because it's 0 velocity because it starts at rest.
Right.
Which equals the velocity final for A.
Yeah, I mean, you'll get the same answer. I mean, that's just a shift in origin, right?
Okay.
If you shift I mean, there's no difference between calling the initial height 10 and the final height 0 as calling the initial height 30 and the final height 20. The difference is the same.
Yeah.
The difference is just that you're not setting yourself up for using the same 0 for the whole problem. You're going to have to shift your origin 3 different times in the problem, which is going to kind of defeat the purpose of it.
I guess I don't understand where the origin is in the equation because I just
the origin is
this
is h. This is not a delta h. It's a height from some reference. So you're setting that in the problem at the beginning. Set h equals 0 to the lowest height of interest, and then go from there. I'm kind of losing people here, so let's talk about that after class if that's still not making sense. Okay. You guys mind if I get back to it? Thanks. Okay, so those are 3 examples, conceptual and then increasingly difficult. You'll find those on the first half of your homework number 7. But we do need to make one major modification to this, and this is to include friction and other forces like friction, which play a very different role in the equation. So the question is, how do you incorporate friction into this? So let me compare work done by gravity to work done by friction. And we're going to find that there is an issue here because these are flagships for 2 different types of forces, 2 different categories of forces that don't play nice in the same way in the energy method. So if I threw a ball up in the air, on the way up, gravity does negative work and removes kinetic energy, but we can be rest assured that when it falls back down, gravity will then also do positive work and add kinetic energy when you fall back down. And we actually have learned that you will gain all the same speed back that you had at the beginning. So all of your kinetic energy that got removed on the way up is given back to you when you fall back down. So here it makes sense to talk about stored energy. You put energy into storage, and then you get it back from storage. So kinetic energy gets traded to potential energy on the way up, and then the potential energy is depleted back into kinetic energy when you fall back down. So potential energy of gravity makes sense. Stored energy makes sense. The stored, of course, implying that if you store it, you can get it back. So let's do the comparable thing with friction. So I'm going to slide an object like this across the table. We see friction does negative work. Does it come back? No, it doesn't. Okay? So unlike gravity, where it takes away energy and then gives it back, friction takes away energy, and that's it. And of course, if I pushed it back, maybe it just needs a little help, well, it takes away more energy, not gives it back on the way there as well. So if we look at the top view of pushing something across the table, friction does negative work on over here and removes kinetic energy. It certainly doesn't come back spontaneously. And if you did give it another push, well, it's going to remove some more kinetic energy. So friction takes away energy and never gives it back. Okay? Which means that if you were to try to do something like define the potential energy due to friction, that doesn't make any sense. You can't say that something stores energy if it always takes and never gives. That energy isn't stored, it's gone, it's stolen. Okay? So friction always steals energy. It never gives it back. So obviously, we can't treat the force of friction in the same way. We can't just incorporate a potential energy due to friction. Here's what we're going to do, just to give you a little bit of a preview. Here's our two forms of energy so far. And gravity, we know, is a two-way street. The trade can happen either way. Friction takes kinetic energy, sends it to heat. Okay? Right? Rub your hands. What becomes of that motion of your hands? It goes into heat. And this is a one-way street. It always goes there, and it never comes back. And so that's going to need a different treatment. First of all, that energy form is not called a potential energy. We'll call it heat. And it has a one-wayness, a one-way street. So we're going to have to acknowledge that not all energy trades can be reversible. So let's knock off there for today. If you have any additional questions on today's material, homework, whatever, I'll be over in my office.